Welcome back, everyone. Um, Today we are dipping a bit into the world of topology. So, as a motivation, let's start with a scenario that we can all relate to, like navigating through a city using a trusty map. So, imagine you are planning, say, an exciting journey through the bustling streets, right? So, you unfold your map, you trace your path, and of course you envision the adventure ahead. But what if the adventure is not confined to just one map? So what if you have a collection of maps, right? Each offering a unique path. So here is the challenge. So you want to piece these maps together in a way that guarantees a seamless, how would I say that, a seamless transition from one to another. So this is so this is so this is um, exactly, what we are diving into today. So this quest for smooth continuity is precisely what the coarsest topology addresses. So it's like creating a simplest set of rules, right, that allow these maps to transition without any sudden jumps. So in essence, we are actually finding the minimal framework for continuity across, this collection of maps. So this is not, this does not only make sense conceptually, but also lays the groundwork for exploring more advanced concepts like weak topology, which will be our topic for the next video. So by the end of this video, I promise you won't just appreciate the beauty of constructing the course's topology, but you will also have a solid grasp of how it is done and the powerful insight it can bring. So so let's start. Right? So assume X is a set. So assume X is a set, of course, without any structure. Let me precise it. Oops. Without any structure. And you have a family, a collection of topological spaces, and say Y I capital I, collection of topological spaces. Topological spaces. So we are also given, a collection of maps. So we are given a collection of maps, say psi I, right? Such that for every I in I, so phi I maps X into yi. So when we consider the following problem. So when we consider the following. So we are faced with, call it, say, problem 1. So put it in color. So we want to construct a topology X, right, on X, right, that makes, so we want to construct the topology the space X, right? That makes all the maps phi I continuous. So if possible, we want to make, we want to find the topology, say calligraphic T, right? That is the most economical, right? In the sense that it has fewest open sets. Good. Well, some of you might be thinking about, endowing X with the discrete topology, but let's try that. So, but it doesn't work, right? So not that. So let me put it in bracket. So not that. If we equip X with the discrete topology, that is, power set, then of course every map is continuous. Then every map phi I is continuous, right? It's continuous. But of course, this topology is kind of, it's really far from being the cheapest. It is in fact the most expensive one. So, so let me write it down. This, and of course, this topology, is really far away from. It's far from being the cheapest. Put it in quote, right? Highlight that. It's far from being the cheapest. In fact, it is the most expensive one. So, as we will see in this, in this lecture, there is always a unique cheapest topology, right, on X, for which the collection of map phi I is actually continuous, and this topology is called the coarsest topology or weakest topology, and sometimes the initial topology associated to the collection phi I. So if so if say Wi, right, it's a subset of Yi, is any open set, then psi I, the inverse, psi I minus 1 of W I is necessarily an open set. I mean, in the topology T. So, however, as W ions, so as W ions through the family of open sets of yi, right? And I runs through capital I, you obtain a family of subset of X, of course. You obtain a family of subset of X, each of which must be open, right? Must be open in the topology T. So let's denote by say u lambda, I mean this family. So let's denote by I said u lambda right here, lambda in which this family. Of course, this family, I mean, doesn't need to be a topology, right? But and therefore we are led to another problem that we call problem 2. Right? Maybe I write it down. Of course, I mean this family need not be a topology. Therefore, we are led to the following problem. Then we call it problem 2. Problem 2. So given a set X, right? So given a set X and a family u lambda, right, of subset of X, family of subset of X. Let me just write it fully. Subset of X, right? We are to construct the cheapest topology, right, on X in which the u lambda, I mean, in which u lambda is open for every lambda. So put it in color. So construct. So this is the task. Construct the cheapest topology. Topology T on X, right, in which u lambda is open for every lambda in which. So in other words, we must find, I mean, let me write it, I'll just again quotation mark. So in other words, we must find, for those who are not familiar with topology, so we must find the cheapest family, say calligraphic F, right? Family of subset of X that is stable on the finite intersection, right? And arbitrary union. And with the property that u lambda belong to F for every lambda in which. Okay, so this was just for more clarity. So the construction goes as follow, right? First, so the construction goes as follows. First, put it in, let me just write first, and I will write like that. So first thing to do, right? Consider finite intersection of sets in U lambda, right? So that is consider, say family of, set of this form lambda belong to gamma, where gamma is nothing else than a subset of weight, right? And gamma is finite. Gamma finite. So in this way, we actually obtain a new family, right? So in this way, we obtain a new family, call it called phi of subset of X, which includes the collection U lambda, right? And which is obviously stable on the finite intersection, which is stable on the finite intersection. Good. But however, this family doesn't need to, to be stable on the arbitrary union. So, however, it need not be stable on the arbitrary union. So therefore, we need to consider another set. So therefore, therefore, we consider next, the family calligraphic F, right, obtained by forming um, arbitrary unions of elements of the set capital phi. So now it is clear that F is stable under arbitrary union, but it's not clear whether F is actually stable under finite intersection. But it is actually the case here. Then, because of the following result that we write in terms of a lemma. So lemma 3.1. So the family F, right, is stable under finite intersection. Good. So for the proof, well, the proof is not complicated, so it's actually easy. And then I actually invite you to try it out. So in fact, what you have to show, you basically have to show that how would I write it? So you have to show that how F, right, which is defined to be the union, right, of, say, we call it O, right? O belong to this capital phi, such that this is a subset of such that this is a kind of subset of yeah. I have to show that. Oops. You have to show that this actually defines. Oops, no, I think I did a mistake somewhere. So not write it this way. After union of element of. So what letter will I use? We use say Q, right? So that Q is actually contained into the subset of. Yeah. So you have to show that F is actually defines a topology if you want. Yes. Yeah, it defines. In fact, you just need to prove that it's actually stable on the finite intersection, because we saw that it's already stable on the arbitrary union. Okay, good. So let's have a remark. Okay, so one cannot, you cannot reverse actually the order of operation in the construction of the topology, the construction of F. So one cannot reverse reverse the order of operation in the construction of F. In fact, it would have been equally natural to start with arbitrary union, right, and then take finite intersection. But the outcome, I mean, is actually a family that is stable under finite intersection, but it is not stable under arbitrary union. So one would have to consider one small arbitrary union, and then the process kind of stabilizes. So in summary, let's have a summary, right? Summary for this construction. Summary. So we found that the open set of topology T, right, are obtained by considering first finite intersection of sets of the form psi I minus 1, phi I minus 1 of Wi, and then arbitrary union. So from this it follows that for every x in X, right, we obtain a basis of neighborhood of X, right, for the topology T by considering sets of the form, so by considering sets of the form finite intersection of phi I minus 1 of Wi. So let's call it Vi, right, where Vi is, I mean, it's a neighborhood of this is a neighborhood of phi I of x in Yi. Okay, so for those who are not familiar with topology, let's have a recall. So recall that in a topological space, right, a basis of neighborhood basis of neighborhood of a point X is just, it's a family of neighborhood, the family of neighborhood, family of neighborhood of X, of course, right? Such that every neighborhood, such that every neighborhood of X contains a neighborhood, contain neighborhood from the basis. So this is basically what we mean when we talk about basis of neighborhood. So in the sequel, related in the sequel, we equip X with our constructed topology. So with the topology T, right? So that is the weakest topology, often called the initial topology as well, or the coarsest topology. Right, okay, associated to the collection phi I. Good. Well, of course, a topology is actually, a topology is useless, right? If it is too complicated for us to deal with it. So, but hopefully, it turns out there is a nice characterization of converging sequences and continuous function from a topological space into a weakly topologized space. So, proposition 3.1, proposition 3.1. Okay, so let Xn, right, be a sequence of point of X, then the sequence Xn converges to X, of course, in this topology, right, if and only if phi I of Xn converges to phi I of X, and this for every I in I. Okay, proof. So, if Xn converges to X, then this implication is rather trivial, right? But let me write it. So if Xn converges to X, then phi I of Xn automatically converges to phi I of X for every I, right? Since phi I is it's continuous. for this topology. Okay, so conversely, now we assume that, phi I of x and converges to phi I of x, and then we want to show that x n converges to x. So conversely, let U be a neighborhood of x, right? So you want to, in order to prove that xn converges to x, you have to find the rank, starting at which all the terms of the sequence actually belong to the neighborhood of x. So we want to find n such that for every n greater or equal than n, right, xn belong to the neighborhood of x. Good. So from our preceding discussion, we may always assume that U has the form. So just write, we may always assume that U has the form U equal to intersection of phi I minus 1 of Vi I belong to say to J, if J being subset of I and J finite. And of course, Vi is a neighborhood of phi of x. Okay, since we have the assumption that phi I of xn converges to phi I of x, right, for each, for every I, right, then we write it here down. Then for each I in J, right, there exists a rank that depends on I, of course, and I in N, such that phi I of xn belong to Vi, provided that write it for provided that n is greater or equal than ni. So it follows from this that for every n greater or equal than n that we define to be the max, right, of the ni I in J, xn belong to U. And then we are done with the proof. So if you feel a bit confused in this last step, so observe that so from this, right, from this, one can say that xn belong to phi I minus 1 of Vi, and this hold for every n greater or equal than ni, and for every I in J. So if you define n to be the maximum, right, of the ni's, so xn then belongs to the intersection, the phi I minus 1 of vi, but the intersection is just u exactly. So just in case you, you felt a bit lost or whatever. Okay, so take another proposition 3.2. 3.2. Okay, so let it's not thread. Good. So let call it Z, right, be a topological space. And let psi, so far I've been confusing psi and phi and those stuff. So let psi be defined from Z to X, right? Of course, end of the weakest topology. So then psi is continuous if and only if and only if phi I composed with psi is continuous from Z into yi, and this should hold for every I in I. Okay, proof. So, of course, if you assume that psi is continuous, then obviously phi I composed with psi is continuous. So, let me hide it. So if psi is continuous, then obviously phi I composed with psi is continuous. For every I, of course. Now conversely, I think this is the most interesting part. So conversely, you have to prove, so conversely, you have to prove, so you have to prove that psi minus 1 of u is open in Z, right, for every open set u in X. But we know that, we know how basis of neighborhood looks like. So but we know that u has the form u is equal to arbitrary union of for those familiar with topology, if you have basis of neighborhood and then you have an open set, then that open set can be written as arbitrary union of element of the basis of neighborhood. So this is exactly what I'm writing down. So U is actually the arbitrary union of the finite intersection. Let me write finite here. the psi I of the phi I minus 1 of wi, where wi is a subset, it's open. Good. So therefore, I think we are basically done. So therefore, the inverse psi minus 1 of u is exactly equal to, the arbitrary union, finite intersection of psi minus 1 of phi I minus 1 of wi. It's a bit, let me drag it a bit to the left, just to create space, of wi. Yeah. So this is exactly equal to, this is the arbitrary union, finite intersection of what of, this is phi I from psi everything minus 1 of wi. Which is obviously open, right? Because this is open by assumption. So let me write it again here. So which is open in Z since every map phi I composed with psi is continuous. And this ends the proof as well as this lecture. So I think now we are somehow well equipped to dive into the weak topology, right? So but we will do that in the next lecture. So thank you once again, and see you in the next video.